as we have applied this mod condition, both are one and the same. So my E plus and E minus becomes E itself. And number of field lines, that is electric field lines passing through that area in that plane sheet is said to be flux. By looking at this diagram, we know that the electric field is parallel to this surface. So at this surface, you have got the flux said to be 0. Hello everyone, I'm Brinda, Faculty of Physics from Vidhyaashram Pre-University College, Mysuru, welcoming you all to session 3 of chapter 1, and the chapter name is Electric Charges and Fields. So here in this session, we are studying regarding the last bit of this chapter, and that we will start up with the electric field at a point on a equatorial line. So here we have to consider a point that is a dipole. Here it is plus q and at a distance of minus q, and that distance can be considered as 2a. Okay, and from the center point, that is from the center O, you have to draw a perpendicular. So, and perpendicular is termed as P, a point P. So, now what is our work? Our work is to find out the effect of positive charge plus Q on point P, or else a negative charge minus Q on point P. The effect, the electric field of those two charges at a single point, that is P, we'll have to calculate. So for that, let us just connect these 2 points with point P. So we have a triangle over here. So now let OP be at the distance of R, and here if you just break the triangle into 2 equal halves, so the charge is at a distance from O and the distance is said to be A. A plus A gives you the total of 2A. Now we have got the value of perpendicular and the value of adjacent, that is opposite and adjacent values are there. So what we don't have, that is the hypotenuse value. So in order to find out the hypotenuse value, what are we supposed to do? We have to apply the right angle triangle formula, that is Pythagoras formula. So what is it exactly? That is, let me consider this point as A and this point as B, A and B. So when we have A and B as well as P in our hands, it's very easy to calculate our right angular triangle formula. That is, you need to know the distance between AP. So square of the hypotenuse is equal to sum of square of other 2 sides. So it can be OP square and OA square. So what is OP? OP is nothing but your R. So I can just take it as R square plus what is OA? OA is nothing but A square. So AP is having a value of root. I am taking my square to the other side. So it is root of R square plus A square. So AP is equal to root of R square plus A square is said to be one of the hypotenuse lines. So I just can write here as R square plus A square. The same thing is applied to BP also. So you can just write it as BP square is equal to, that is square of hypotenuse is equal to sum of square of other 2 sides. So I can just consider OP square and the other side as OB square. So what is OP square? It is R square plus OB is what? It is A. So I can just consider it as A square. So your BP becomes, which is equal to root of R square plus A square. So here we have our hypotenuse value, that is AP as well as BP value. So we have the value for all 3 sides of a triangle. So now what are we supposed to do? We have to check check the electric field at that point. So in order to know that, we know the direction of the positive charge as well as negative charge, that is electric field direction with respect to two of the charges. So when you just draw it, electric field, since it is a positive charge, it moves away. So I can just draw like this. And negative charge, it is towards negative charge, so I can just draw along this line, and there is a electric field which is parallel to the baseline, and we have two perpendiculars to the base. Okay, so here it is, along the perpendicular line we have two fields. Call it as E sine theta, that is E plus sine theta, and E minus sine theta. Again we have E sine theta, call it as E1 and E2. E1 sine theta and E2 sine theta. And here we have E1 and E2, whereas this horizontal component can be called as E1 cos theta and E2 cos theta. So these are the components of a triangle over here. This is where we identify the electric field at a point on an equatorial line. So this is how we just find out. The basic concept is, first of all, you will have to identify the hypotenuse value. So after this, what are we supposed to do? So we know that the electric field is calculated as E is equal to, that is the electric field of a positive charge at point P. So positive charge is this. The electric field which is from this charge at point P is actually given as E positive, and you know that the field formula 1 by 4 pi epsilon naught q divided by the square of the distance. Distance can be any numbers whichever is given over here, or any alphabetical terms which is given over here. So I can write it as E positive is equal to 1 by 4 pi epsilon naught Q. Q is the positive charge. It is plus Q. So I'll just leave the plus as it is, divided by the square of the distance between them. Them means what? It is plus Q and point P. So square of the distance can be given as root of R square plus A square, the whole square, and N cap. N cap. Why am I writing N cap? That is the vector quantity. Okay. In order to balance two sides of the equation, I just give any alphabetical term with a cap upon it, which is known as a unit vector. So any alphabets with a cap on it is said to be a unit vector. So now here we just consider it as your square and square gets cancelled. So E plus becomes 1 by 4 pi epsilon naught Q divided by R square plus A square. So this is one of the term. And next, similar way we have to go on with the minus sign. So it is minus Q. So E minus is equal to 1 by 4 pi epsilon naught Q divided by, same thing goes up to here, because even this distance or also same thing, that is root of R square plus A square, wherein you're squaring the distance between them, square root cancels with square as in this equation, and what remains is R square plus A square. Okay, so now you have got your unit vector N cap, and here it is a unit vector what you can write over here. And the same unit vector is present over here. Since it is minus Q, it's a negative charge, I can just write it as minus N cap. So you have got your two equations in your hands. So now you can just equate it as mod of this equation is equal to mod of this equation. The mod condition is always just for the sake of deleting your negative sign. So only difference between these two equations is only this negative sign. So in order to cancel that, you just apply mod condition to it. So mod of positive electric field to mod of negative electric field, both are equal to 1 and the same, and it can be just E. So now You have got these are the initial conditions, preliminary steps what you have to take for this derivation, and this is one of the most important derivation and it's for 5 marks. Okay, so now we have this set of diagram in a parallelogram form. So when that is the case, we have to take up the parallelogram law of vector additions formula. So what formula it has got? So I can just write it as R is equal to root of A square plus B square plus 2AB cos theta. So again I'll write R is equal to root of, what is A? I can just write it as E plus square plus E minus square plus 2E plus E minus cos theta. A is E plus and B is E minus. As we have applied this mod condition, both are one and the same. So my E plus and E minus becomes E itself. So what we have now, R is equal to root of E plus E, both are squares, plus 2E square cos 2 theta. So we have R is equal to root of E square plus E square is 2E square plus 2E square cos 2 theta. So R is equal to root of, taking common out from these two set of equation, it becomes 2E square. So I have 1 plus cos 2 theta, which I can write it as E 2E square. 1 plus cos 2 theta can be written as 2 cos square theta. So what happens to this 2 and 2? It combines and we get 4E square cos square theta. Your square cancels with this square and this square, and root of 4 is always, that is root of 4 is always 2. So I can just write this as R is equal to 2E cos theta. So we have this equation in our hands. Correct? So we have 2, we have E and we have cos theta. So what is the value of E when E is over here? The value is either E plus or E minus, both are merged together as in the previous set of equation, and you can write either of the equation in that concept. That is R is equal to 2 into 1 by 4 pi epsilon naught Q divided by R square plus A square, and we have our cos theta in our hands, which is equal to, cos theta is adjacent by hypotenuse. So formula of cos theta is adjacent by hypotenuse. So what is the adjacent over here? If this is hypotenuse, this is adjacent, and this line, that is a perpendicular line, is said to be opposite. Okay, so what is adjacent A by hypotenuse is root of R square plus A square. So I can just write it as adjacent by hypotenuse root of R square plus A square, which can be rewritten as cos theta is equal to A divided by R square plus A square the whole half. Okay, so when this is a case, it is like you can just write the same thing, that is substitute for cos theta. So you have A divided by R square plus A square the whole 1 by 2. So 1 by 2 and to the power of 1. So you have 1 by 2 plus 1, taking LCM you will just get 3 by 2. So now rewriting this equation, you have R is equal to 2 into 1 by 4 pi epsilon naught Q into A divided by R square plus A square the whole 3 by 2. As we had discussed in the previous session, that is all about the dipole moment. So what is this dipole moment? It is P vector is a dipole moment. It is charge and the distance between the charges. So I can just mention it as charge is represented in a standard form, that is Q, and distance between them is 2A. So 2AQ. So here I can just substitute this as, so now according to the dipole moment we have 2A into Q. So 2A into Q can be taken from this term, and we can rewrite this as E is equal to, let the resultant be written as the total electric field which is present over here. So 1 by 4 pi epsilon naught, and 2qa can be written as dipole moment divided by r square plus a square the whole 3 by 2. Okay, so and we have this equation given by, that is E is equal to, if suppose your R is very much greater than A, then A can be neglected. On neglecting this A, you will have 1 by 4 pi epsilon naught P vector divided by R, square and square cancel, so it is just R cube what will be present over here for you. So that is all about your electric field at a point on a equatorial line. So here, now let us talk about the charge distribution. So what is meant by charge distribution? It is distribution of charges. It's there in the statement itself. So charge distribution is like distributing the charges over the surface area of any object. If suppose this is an object, your charge distribution is only on the surface, and at the center of the object there is no charges present. Okay, so charge distribution can be of three types: linear charge density, surface charge density, and volume charge density. So for that we have got linear charge density. Anything with regard to the length, we talk about linear charge density. So we have linear charge density given as lambda. So lambda is equal to charge per unit length of a wire is said to be the linear charge density. So how can you give the SI unit of this equation? Charge means coulomb, length is meter, so it is coulomb meter inverse will be the SI unit for linear charge density. Similarly, for the surface charge density, we have got the charges which is distributed on the surface of a plane sheet. So how can you give this? Surface charge density is given by sigma. So surface charge density sigma is equal to charge per unit area. In that area, what is the charges present? So here you can give this SI unit as coulomb and meter square, which is equal to Cm minus 2 will be the surface charge density. Next we have got the volume charge density. Here also we are talking about the same, the charge density, that is it is represented by rho, which is equal to the charges present per unit volume. Okay, so now here you have got your SI unit as C and M cube. For volume, it is always cube of the length, that is meters, which is given in meters, C by M cube. So I can just write the rho's SI unit, that is volume charge density's SI unit can be written as coulomb meter minus cube. Okay, that is not centimeter, it is coulomb meter minus 2. Okay, so after this we have Gauss law. So what is meant by Gauss law? Gauss law is always the one where we talk about the flux. Okay, the flux. Flux means what? If I have given you a sheet or an object and certain area, you will have to focus on the certain area, and number of field lines, that is electric field lines passing through that area in that plane sheet is said to be flux. So flux is total number of electric field lines passing through that area. Okay, so flux here is the total flux over a closed surface. Over a closed surface in a vacuum condition is equal to 1 by epsilon naught times the charge which is enclosed by that surface. Okay, so epsilon is equal to 1 by epsilon naught times the charge. So Gauss law can be given by this equation, that is flux is equal to charge divided by epsilon naught. So this can be the Gauss law statement. So having this flux, we will have to derive three of the applications as given here, and in order to derive those applications, we have to consider an imaginary surface. We have always got an imaginary surface in order to calculate the field at a certain point because of the infinitely long wire, or else the plane sheet, infinitely charged plane sheet, or else the infinitely charged this, or else a spherical shell. In order to calculate the uniformly distributed charges which is responsible for the electric field, so here we have got the surface, which is called as the imaginary surface, and it is also called as Gaussian surface. So what is a Gaussian surface? It is a closed surface which we choose in order to check out the electric field at a point, either by using linear charge density or else a surface charge density in an object, that is the applications of Gauss law. In order to apply for the Gauss law, we just have this Gaussian surface. So Gaussian surface is what? It's a closed surface chosen for the applications of Gauss law. So what are those applications? So you can see the applications, 3 of the applications here, that is electric field due to an infinitely long straight uniformly charged wire, electric field due to uniformly charged infinite plate sheet, and electric field due to a spherical shell. This is also uniformly charged. The common point in these 3 of the applications is nothing but uniformly charged conductors, okay? But one we calculate it as infinitely long wire, the second one is infinitely charged plane sheet, and another one is a spherical shell. The common term is uniformly charged objects. So now, having these concepts, let us just derive for electric field due to an infinite long straight uniformly charged wire. So we have a infinitely straight uniformly charged wire which is taken in a horizontal way, and covering that we have got Gaussian surface which we are considering over here, and that Gaussian surface is nothing but a cylindrical in shape, which has got the length L and its area is dA as given over here. Okay. So now we are checking on to electric field due to an infinitely long straight uniform charged wire. So let me consider a uniform straight wire with a positive charge, that is uniform charge, and it is infinite wire. So when this is a case, consider a perpendicular point P from a distance O, and it can be said as R, the distance is R, and consider 2 line elements over here in the infinite wire which can be called as P1 and P2, which is joined over here P. And the electric field due to P2 will be E2 and P1 will be E1. So this is the extension of it. So it is E, electric field at a point E. In order to calculate this, we have to consider a Gaussian surface. So here this can be the circle since it is the origin. So it can be told as it's a radius R. Okay, consider a Gaussian surface, that is a cylindrical Gaussian surface for the same infinite wire. I am redrawing this figure. So this can be figure A and this is figure B which I am considering. So here I am drawing a Gaussian surface, and the Gaussian surface has got a length as L. And the point here, the same point I am drawing over here, that is P, and it is at a distance R from O, and this is the imaginary Gaussian surface. So having this concept, let us just see how to calculate the surface area. Surface area is equal to 2 pi r is this area for the cylinder over here circle, that is 2 pi r is a surface area into, what is this length? It has got as L, okay, 2 pi r into L. So surface area is 2 pi rl. Now we'll have to calculate the flux. Flux at the surface is nothing but the field, electric field into along this area. Area is what? 2 pi RL. So that can be the flux in the surface. So this is not with regard to your Gauss law. This is all because of this diagram whichever we are drawing here. Now let us consider the flux at the end. So flux at the end, since it's parallel to the field, so it is 0. So you have got total flux is equal to flux at the surface and flux at the ends together. It is nothing but E into 2 pi R into L. So having the same concept, let us just equate along with the Gauss law. So according to Gauss law, you have charge is 1 by epsilon naught times. So this is, you can just call this equation as equation 1 and the next equation as equation 2. So equating 2 and 1, you have got Q by epsilon naught is equal to E into 2 pi RL. So you're talking about infinite long straight wire. Okay, so long straight wire means we are talking something about length, and so what is that length? Length lambda is equal to linear charge density, the charge per unit length of a wire. So charge is equal to lambda into L. So lambda into L is being substituted over here, divided by epsilon naught, which is equal to E into 2 pi r L. Your L gets cancelled with L. So what is remaining is just E. Get it towards your left hand side, which is equal to, just take lambda divided by 2 pi r and epsilon naught. So this is the equation. Lambda by 2 pi r epsilon naught can be the electric field in case of infinitely long straight current carrying conductor. Okay, so it's very easy, and this set of applications of Gauss law is also important in the exam point of view. They might ask either of the three. So next let us move to electric field due to uniformly charged infinite plane sheet. So here we are focusing on the plane sheet. So we have got a plane sheet over here, and the cylindrical Gaussian surface is being considered. Okay, and the electric field is always moving perpendicular to the conductor. Okay, since here we had taken, this is the conductor, electric field was perpendicular to the flow of the charges. So here we are considering a Gaussian surface, that is cylinder, and here we have infinite plane sheet. So this infinite plane sheet has got a electric field which is perpendicular to it, and it is represented as E, and this is said to be the area. So on considering this plane sheet, so now by looking at this diagram, we know that the electric field is parallel to this surface. So at this surface, you have got the flux set to be 0. But at the ends, for this end, this electric field is said to be perpendicular to this end, that is at 90 degrees. So because of which, at the ends we have got the flux given as field into area. So I can just write it as electric field into area from one side, and again electric field into area. So here we are considering two set because it is two ends, okay, of the Gaussian surface. So now you have got at the ends 2EA. So this can be called as equation 1. So the total flux from this diagram we have surface and flux at the end 0 plus 2EA. So total flux is 2EA. Call this as equation 2. Now we have equation 2 in our hands. So now we will have to equate this equation, that is the flux, by looking at this diagram with the flux given by Gauss law. And that can be called as flux is equal to Q by epsilon naught. So we have Q divided by epsilon naught is equal to 2 into E into A. Okay. So for this Q by epsilon naught 2EA, what is Q? Here we are talking about plane sheet. So plane sheet has got charges that is uniformly distributed, and it can be called as surface charge density, which is given by sigma is equal to charge per unit area. So your Q can be written as sigma into A. Okay, so it is sigma A divided by epsilon naught, which is equal to 2 into E into A. A cancels with A, so what remains is E is equal to sigma by 2 epsilon naught. So this can be the equation for your plane sheet. Okay, so it's very easy. Just you'll have to get the flux by with the help of a diagram and equate the same flux with the Q by epsilon naught, that is Gauss law. So next, going on to electric field at a point outside the shell, and the shell, whatever here outside the shell, whichever imaginary surface you're considering will be Gaussian surface, and here the Gaussian surface you're considering will be a spherical surface. So here you have got a sphere. So this is just in order to mention the center point, okay. So circle's center. So this circle is at a distance r, that is capital R, and the Gaussian surface is at the distance small r. So since it is a spherical surface, the electric field is radial everywhere. It is always perpendicular to this middle point. Okay, so it is completely radial. These are the red lines depicts the electric field. Since it is radial everywhere, the surface area, whatever is there, it never becomes zero. So for Gaussian surface, you are calculating the flux. So flux is equal to, before that, area is said to be 4 pi r square. So here we are considering the area for the Gaussian surface. So the radius of the Gaussian surface is small letter r. So 4 pi r square. Area is equal to 4 pi r square. So now you have got your flux, and flux is nothing but the field into area 4 pi r square. So this set can be called as equation 1. Now equate your Gauss law, that can be called as flux is equal to Q by epsilon naught. So equate this and this. So you have it as Q by epsilon naught is equal to E into 4 pi r square. So now you have got it as Q. What is that Q? Q is nothing but, here we are considering the surface charge density again, because the uniformly distributed charge is only at the surface and not at the center. Remember this point. The surface charge density lies only at the surface and not at the center over here. So you have got your Q is equal to sigma into A, surface charge density. So Q is sigma into A by epsilon naught, which is equal to E into 4 pi r square. So what is this area for this set of circle, that is r? It becomes 4 pi capital letter R square. So it is shown that sigma 4 pi r square divided by epsilon naught, which is equal to E into 4 pi r square. 4 pi cancels with 4 pi, and what remains is electric field. E is equal to sigma into r square divided by epsilon naught into r square. So you have got this equation. So now substituting for sigma, you have got, either you can end it up here itself, or else you can continue. Sigma is E is equal to charge per unit area, that is surface charge density, epsilon naught r square by small letter r square, and you can substitute for area as 4 pi r square, that is given as E is equal to Q by, you're talking the area is all about this circle, that is the inside circle, the solid figure, not the imaginary condition. So you have got your 4 pi r square epsilon naught r square divided by r square cancel. So whatever is remaining, that is the remaining expression. So that is all about your electric field at a point outside the shell. Next is same spherical shell electric field itself you will have to calculate, but now it is like inside the shell. So electric field at a point inside the shell, so that you will consider the Gaussian surface inside. This can be called as Gaussian surface. But here in this case, inside the sphere, I have already told you the charge is 0, therefore the electric field E is said to be 0 in this case. That is electric field at a point inside the shell. Since the Gaussian surface is placed inside the shell, calculating the field inside the shell is always E is equal to 0. So here electric field is 0. This is simple, isn't it? So here in today's class, we have discussed about the electric field at a point in an equatorial plane, as well as Gauss law, its applications, charge distribution and derivations of those applications. What is the electric field? It's certain, that is infinitely charged wire, plain sheet, as well as spherical shell. So that's all for today. Let us all meet in the next session with a numerical session of the same chapter. Until then, have a good day. Thank you.